welcome back to a quiet evening with the sky. Before we go any further, if you want a brand new Earth topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. Tonight, we drift slowly into one of the oldest puzzles our species has ever tried to solve: the strange and unpredictable behavior of the air that surrounds us. Picture, if you will, the planet as a single thin shell of weather. Imagine looking down at it from a great height, watching the swirling white of clouds drift across deep blue oceans and pale brown continents. That thin shell, the part where weather happens, is only about 10 miles deep. It is thinner in scale than the skin of an apple. And yet inside that fragile layer, almost everything we have ever called weather has formed and faded and formed again. For thousands of years, people have watched this layer with quiet awe. They have looked up at the slow build of a thunderhead and tried to guess when the first drop would fall. They have sniffed the air for the metallic scent of an approaching storm. They have noticed how the light turns green before hail, how the wind goes still before something larger arrives. Weather is one of the few mysteries that has been with us in every generation, in every village, on every continent. And still, after all that watching, after all those centuries of careful notes, the sky surprises us. That surprise is what we want to sit with tonight. Not the ordinary rain, not the gentle snowfall, not the soft summer breeze. We want to wander into the corners of the atmosphere where things behave in ways that even modern science struggles to fully explain. Rains of fish, glowing clouds at the edge of space, lightning that takes the shape of a slow drifting ball and floats through a kitchen window. Hailstones the size of melons that fall from clear skies. Snow that rolls itself into neat cylinders across an empty field, with no human hand to shape it. Some of these events have, over the years, been partly understood. Researchers have proposed careful theories, ran the numbers, and pointed to likely causes. But some of these events remain, even now, only half answered. There are competing ideas about how they form. There are eyewitness reports that scientists cannot fully match to the data. There are recordings that show something happening, and no agreed model that explains why. This is the open question we will rest in tonight. Which of Earth's strangest weather events do we actually understand, and which still leave meteorologists shaking their heads in quiet wonder? The sky, you see, is a system of almost unimaginable complexity. Warm air rises and cool air sinks. Water turns to vapor and back again. The spinning of the planet bends the wind into great curling patterns. Dust from a distant desert drifts thousands of miles and seeds a cloud over an ocean. A volcano in one hemisphere can change the color of sunsets in the other. Every part of this system touches every other part, and a small change in one place can ripple outward in ways no model can fully track. That is why prediction, even with our best satellites and our fastest computers, has limits. We can forecast a storm a few days out. We can map the path of a hurricane with growing skill. We can warn a town that a tornado may form within the hour. Yet the truly odd events, the ones that fall outside the usual categories, often arrive without warning and leave without clear explanation. They show up in a single field, in a single moment, and then they are gone. Over the next few hours, we will wander slowly through these oddities. We will visit the reigns of strange and unexpected things. The hum that distant storms make in the bones of the earth. The silent flashes of light that flicker above thunderclouds in the high atmosphere. We will pause at the edges of glaciers, where the ice forms perfect circles. We will stand quietly at the rim of a dust storm, crossing an ocean, and throughout, we will hold the same gentle question in our minds. How much of this do we really know? How much of it still belongs to the sky alone? So settle in. Let the lights go low. Let your breathing slow. There is no urgency tonight. No answer we need to reach. No test at the end. There is only the long, slow weather of a living planet and the soft, patient wonder of a question that has not yet closed. Let us begin. Before we wonder about lightning that rolls in slow, glowing spheres, or storms that bloom in dry mountain air, it helps to start with something simpler, something that has puzzled people for as long as people have stood outside and looked up. Rain that is not just rain. For most of us, rain means water, Soft drops falling from gray clouds. A familiar sound on the roof at night. But across the long memory of weather, the sky has dropped other things too. Fish, no longer than a finger, scattered across a small village square. Frogs, still alive, hopping in the wet grass after a storm. Soft pink dust coating cars and windows. Tiny pieces of ice the size of dinner plates. Threads of something thin and white, drifting down like spider silk. These reports are not just folklore. Many have been confirmed by scientists who arrived afterward to gather samples. In 2010, in a small town in northern Australia, hundreds of small silver fish fell from the sky over the course of 2 days. In southern India, a strange red rain fell for weeks in 2001, staining clothes and rooftops a deep, rusty color. In Mexico, in 1997, a chunk of ice the size of a sofa cushion fell from a clear blue sky and shattered a parked car. No storm, no cloud, no easy explanation. The simplest way to think about strange rain is this: air is not still. Even on calm days, the sky above us moves in slow rivers and sudden columns. Warm air rises, cold air sinks. Inside a thunderstorm, the air can rush upward at speeds faster than a car on the highway. That rising air, called an updraft, is strong enough to lift things off the ground. Small things, light things, sometimes not so light. A waterspout passing over a shallow pond can pull up water, and with the water, small living creatures. Fish, tadpoles, tiny shrimp. The spinning column holds them in the air for minutes, or even longer. Then the storm moves inland, weakens, and lets its cargo fall. To someone standing in a field a few miles away, it looks like the sky has rained animals. That is one theory, and the most common one. It explains many cases, but not all. The pink and red rains are different. Often, they come from dust lifted thousands of miles away. The Sahara Desert, which covers an area larger than the United States, sends huge plumes of fine red sand into the upper atmosphere. Winds carry that dust across oceans. When it mixes with rain clouds, it falls back to earth, tinted the color of clay. People in Europe sometimes wake to find their cars dusted in Saharan sand. even though the nearest desert is far across the sea. That much scientists understand well. But the red rain of Kerala in southern India is still debated. The water held tiny red particles that looked, under a microscope, almost like living cells. Most researchers believe they were spores from a local type of algae, lifted into the air by some unknown process. A smaller group has suggested other possibilities. The mystery has never been fully closed. Then there are the great chunks of ice. Scientists call them megacryometeors, which simply means very large ice meteors. They are sometimes the size of a basketball, sometimes much bigger. They have fallen on rooftops, on fields, on quiet roads, in places where there is no thunderstorm overhead, no plane passing by, no clear source at all. One idea is that they form in unusually cold layers high in the atmosphere, building up slowly like a hailstone that never gets to fall until it is enormous. Another idea is that they come from ice that breaks off aircraft. A third possibility raised by some researchers is that something about the high atmosphere is changing in ways we have not yet measured. The evidence is incomplete. What all these strange rains share is a simple, humbling truth. The air above our heads is doing more than we can see. It is lifting, swirling, carrying, mixing, sorting. It is pulling things from one place and setting them down in another. The sky is not just a backdrop. It is a slow, restless river, and sometimes what it carries is unexpected. For tonight, you do not need to know which theory is right. You can simply rest in the knowledge that for thousands of years, in many places, people have walked outside after a storm and found something puzzling on the ground. They picked it up. They wondered. And the wondering passed down through generations, all the way to this quiet moment and to you. Of all the strange things that fall, glide, or flicker across our skies, few have caused as much quiet puzzlement as the small glowing sphere known as ball lightning. It appears, by all accounts, during or just after a thunderstorm. Witnesses across hundreds of years describe a softly glowing orb, often the size of a grapefruit, sometimes as large as a beach ball. It drifts slowly through the air, It floats down chimneys, slides along windowsills, hovers in barns and kitchens and ship cabins. And then, after a few seconds, it fades, vanishes, or pops with a soft sound, leaving almost nothing behind. The riddle is simple to state and very hard to answer. We do not fully know what ball lightning is or how it forms. We do not know why it lasts so long when ordinary lightning lasts only a flash. We do not even know with full confidence whether every reported sighting describes the same phenomenon or several different ones that only look alike to the human eye. The story of how this thing comes to exist begins, most likely, with a thunderstorm. A storm cloud builds tall and dark, charging itself with electricity in ways scientists still work to fully describe. A bolt of regular lightning strikes the ground, and then, in the moments after that strike, sometimes, rarely, something else appears. A small luminous ball, glowing red, orange, yellow, white, or pale blue, floating where no ball should float, moving in ways no flame should move. For centuries, sailors spoke of it gliding along the masts of wooden ships. Farmers spoke of it rolling through open windows. Monks wrote of glowing spheres entering chapels during thunderstorms. The reports come from every continent, every culture, every century with written records. That alone suggests the thing is real, even if we cannot yet pin down its nature. One leading theory begins with the soil. When a lightning bolt strikes the ground, it heats the earth instantly to temperatures hotter than the surface of the sun. In that flash, tiny grains of silicon locked inside the soil may be vaporized, then ejected upward as a fine cloud of glowing particles. As those particles meet the cooler air, they may slowly oxidize, burning gently, giving off light for several seconds. A small, drifting, softly burning cloud of vaporized soil. That is one possibility. Another theory leaves the ground entirely. Some researchers wonder whether ball lightning is a kind of plasma, a pocket of charged gas, somehow held together by its own magnetic field, like a tiny, self-contained knot of electricity. In a laboratory, plasma normally falls apart in fractions of a second. So, if ball lightning is plasma, something must be holding it together far longer than physics seems to allow. What that something is remains an open question. A third idea points to microwave radiation. During certain lightning strikes, brief bursts of microwave energy may be released. Those microwaves, the theory says, could become trapped inside a thin bubble of ionized air, glowing from within like a lantern. When the bubble breaks, the light goes out. It is an elegant idea. It also has not yet been fully confirmed. There are quieter ideas, too. One suggests that ball lightning is not in the sky at all, but in the eye of the witness, a kind of visual afterimage produced when the brain is briefly affected by the strong magnetic fields of a nearby strike. That would explain why the spheres are so often seen just after the flash, and why they seem to follow the viewer's gaze. But it does not explain the cases where many people in different places saw the same glowing object, or where the object left scorch marks on a wall. So, the origin story of ball lightning is really several origin stories, sitting side by side, none of them fully proven. A burning cloud of vaporized earth, a knot of self-contained plasma, a bubble of trapped microwaves, a trick of the brain. Perhaps the truth is one of these. Perhaps it is a combination. Perhaps, when we finally understand it, we will find that the term ball lightning has been describing 2 or 3 quite different things all along, each born under slightly different storm conditions. The conditions that have to be exactly right are still being mapped. A storm of a certain strength, a strike at a certain angle, a soil of a certain composition, maybe, or an atmosphere with just the right humidity. Researchers have produced small glowing spheres in laboratories using high voltage equipment and silicon wafers. And those spheres behave in some ways like the real thing. In other ways, they do not. The recipe remains incomplete. The riddle stays open, glowing quietly. High above the everyday clouds, in the cold upper edge of the sky, something quietly strange happens on certain summer nights. A thin, silver blue veil appears against the deep twilight. It glows softly, as if lit from within. These are noctilucent clouds, and they live higher than any other clouds on Earth. They drift about 50 miles above the ground in a layer called the mesosphere, where the air is so thin it can barely be called air at all. For most of human history, no one wrote about them. The oldest clear records only began in the 1880s, not long after the great eruption of Krakatoa filled the sky with dust. Some early observers wondered if the volcano had somehow seeded these glowing veils. Others guessed they were simply rare clouds that had always been there, just unnoticed. The question of where they truly came from has stayed open for more than a century. To make any cloud, you need three things. You need water. You need something cold enough to freeze it. And you need tiny specks for the ice to gather on, called nuclei. In the lower sky, those specks are easy to find. Dust from deserts, salt from oceans, soot from fires, pollen from forests. The sky near the ground is rich with material. But 50 miles up, the air is almost empty. So where does the dust come from up there? And where does the water come from? In a place so dry it should hold almost none. One leading idea is that the tiny specks are not from Earth at all. They may be the ground-up remains of small meteors. Every day, tons of tiny rock and metal grains drift down into our atmosphere from the wider neighborhood of the solar system. Most are no bigger than smoke particles. They burn up, soften, and slowly settle. Some researchers believe these meteor crumbs become the seeds for noctilucent ice. If that idea holds, then every glowing summer cloud is partly built from material older than the Earth itself, forged in the long, slow furnaces of ancient stars that died before our sun was born. The water is another puzzle. The mesosphere is one of the driest places connected to our world. Yet there is just enough moisture in certain seasons to freeze onto those tiny grains and form crystals of ice so small they can only be seen when the sun, already set for people on the ground, still lights them from below. One theory suggests the water rises slowly from the lower atmosphere through gentle, large-scale circulation. Another suggests some of it forms when methane, drifting upward from the surface, breaks apart in sunlight and releases hydrogen that joins with oxygen. Both ideas may be partly right. The full answer is not yet settled. What unsettles some scientists is that these clouds seem to be appearing more often, and farther south than they did a century ago. Once they were a rare sight, only seen near the poles. Now, they sometimes glow above places where people have never seen them before. One possibility is that more methane in the air is producing more high-altitude water. Another possibility is that the mesosphere is slowly cooling, even as the lower air warms, allowing ice to form more easily. A third possibility is that rocket launches are leaving water trails high in the sky. The honest answer is that researchers are still weighing all three. There is something fitting about a cloud made of star dust and faraway water. The iron in Earth's core was forged inside dying stars long ago. The gold in the deepest veins of rock was scattered by ancient explosions across space. Much of the water in our oceans may have arrived on icy comets and small rocky bodies during the early, violent youth of the planet. Even the carbon in our bones traveled through cosmic clouds before settling here. So when a thin silver veil glows in the summer twilight, it may be a quiet reminder that the materials of our weather are also the materials of everything else. The strangeness does not end with where these clouds come from. Their patterns ripple in delicate waves, like sand on a windswept beach, as if some great slow tide were moving through the upper air. The reasons for those patterns are still being mapped. Some involve gravity waves rising from mountains and storms far below. Others involve currents in the mesosphere that we can barely measure. For now, the silver clouds keep their secrets. They appear, they glow, they fade with the deepening night. And somewhere in their tiny ice grains, a question remains, drifting quietly above a sleeping world. Somewhere on Earth, right now, a storm is humming. Not loudly, not in a way most people will ever hear with their ears, but the planet itself is listening. Deep below the noise of cities and the rustle of trees, there is a slow, steady pulse in the air, a low vibration that travels around the world and never quite stops. Scientists call it the Schumann resonance. It is the sound of lightning, smoothed and stretched until it becomes something almost like breathing. To understand it, picture the space between the ground and the upper sky. That space forms a kind of hollow shell. The bottom of the shell is the earth. The top of the shell is a layer of charged air high above the clouds called the ionosphere. Lightning bolts crack open the air below, and each flash sends a wave of energy bouncing inside that shell. The waves go around the planet again and again before they fade. The hum is the sum of all of them. Every storm everywhere, adding its small voice to the chorus. This is one of the invisible forces that shapes our weather. Not heat, not pressure, but charge. The slow movement of electricity through the atmosphere. Most of the time, we cannot feel it, but it is always there, like a quiet heartbeat in the sky. The forces that build storms are simple to name and strange to follow. Heat rises, cold sinks. Air with more moisture is lighter than air with less. The sun warms one patch of ground more than another, and the warmer patch sends a gentle column of air upward. That column cools as it climbs. The water inside it gathers into droplets. The droplets gather into clouds. And inside the clouds, tiny pieces of ice rub against each other, scraping off small bits of charge as they fall and rise. That rubbing is what builds lightning. The top of a thundercloud becomes positive. The bottom becomes negative. The ground below picks up a positive shadow that follows the storm like a faithful dog. When the difference grows too great, a path of charged air opens, and the bolt jumps. In a single flash, more energy moves than a small city uses in an hour. But here is where the question opens. We know roughly how lightning is born. We do not fully know why some storms produce so much of it, and others, almost none. We do not know why certain bolts travel sideways for tens of miles, while others stab straight down. We do not know why some thunder rolls for half a minute, while others end in a single sharp clap. The forces at work are the same. The results are not. Pressure plays its own quiet role. Air has weight, even though we cannot feel it. A column of air pressing down on the ocean weighs as much as a column of water several meters deep. When that pressure drops in one spot, air rushes in from the sides to fill the gap. The rushing air is what we call wind. A small drop in pressure makes a breeze. A large drop makes a hurricane. The mystery is how small changes in heat far away can ripple through the air until they become storms on the other side of the world. There are theories about this rippling. One idea is that the ocean and the atmosphere talk to each other in slow, looping conversations, with warm water nudging the wind, and the wind nudging the water back. Another idea is that the upper atmosphere holds its own patterns, vast and slow, that shape what happens far below. Both ideas have evidence. Neither tells the whole story. The conversation between sea and sky is still being learned. Gravity is part of it too. Gravity is what pulls rain back down. Gravity is what keeps the heavy, cold air near the ground when warm air slides over the top. That layering, with warm above and cold below, can trap fog for days. It can build the strange calm that comes before a storm. It can hold smoke close to the earth until the wind finally lifts it. And through all of it, the planet keeps humming. The Schumann resonance pulses on, somewhere around 8 cycles per second, a number that has not changed much in the time we have been measuring it. Some researchers wonder whether this hum carries information about storms in faraway places. Others wonder whether it shifts in ways we have not yet learned to read. The hum is gentle. The question beneath it is not. For tonight, it is enough to imagine that slow pulse in the air around you, the quiet bookkeeping of every storm on Earth. Snow in a warm place feels like a small breaking of the rules. We expect snow in cold mountains, in northern forests, on the tops of high peaks where the air thins and the temperature drops. We do not expect it in the desert. We do not expect it on a beach. And yet, every so often, the sky lets soft white flakes drift down over places that have never seen winter in any normal sense. To grasp how strange this is, picture the Sahara. The Sahara covers about 3.5 million square miles of sand and stone. That is roughly the size of the entire United States. Most days the temperature there climbs past 100 degrees Fahrenheit. The ground bakes. The air shimmers. And still, on a handful of recorded mornings in the town of Ain Sefra in Algeria, snow has dusted the orange dunes. Thin sheets of white have wrapped around sand that only days before was hot enough to burn bare skin. The contrast is almost impossible to hold in the mind. Snow has also fallen in the deserts of Saudi Arabia. It has fallen on the dry edges of the Atacama in Chile, one of the driest places on Earth, where some weather stations have never recorded a single drop of rain in their entire history. It has fallen in rare years in the low, warm parts of southern Texas, in Florida, even on the beaches of the Gulf of Mexico. Imagine palm trees with snow caught in their fronds. Imagine cactus spines crusted in frost. These scenes are real. They have been photographed, and yet they still feel like dreams. The scale of the temperature swing is what stuns the senses. In Ain Sephra, the summer high and the winter snowfall can be separated by nearly 130 degrees Fahrenheit. That is the difference between a hot bath and a sheet of ice. The same patch of sand experiences both in the same year, under the same sky. The grains of quartz expand in the heat and contract in the cold, over and over, century after century, slowly cracking themselves into smaller and smaller pieces. Snowflakes themselves are tiny in a way that is hard to picture. A single flake is usually less than half an inch across. Hold one on a dark glove, and it looks like a fleck of lace. Yet, when enough flakes gather, they can blanket a continent. 1 cubic foot of fresh, fluffy snow weighs only about 5 or 6 pounds. The same cubic foot, packed and wet, can weigh 20 pounds or more. A snowstorm covering a single square mile to a depth of 1 foot moves the weight of small mountains across the sky. The atmosphere, which feels like nothing when we walk through it, is in fact carrying these mountains all the time. The question of why snow sometimes falls in warm places is not fully settled. One idea is that a cold pocket of upper air, called an upper level trough, sometimes plunges far south of where it usually wanders. It drags freezing temperatures down with it for a day or two. Another idea points to shifts in the jet stream, that fast ribbon of wind that circles the planet about 6 miles up. When the jet stream loops and wobbles, it can pull Arctic air into deserts and tropical coasts. Some researchers wonder if these loops are growing more common as the planet warms, since a warmer Arctic may weaken the jet stream and let it sag further south. Others argue the data is still too thin to say. The mechanism is partly known. The pattern across decades is still an open question. There is something gentle in thinking about scale this way. The Sahara is older than memory. Parts of it have been desert for at least 7 million years. In all that time, snow has touched its dunes only a handful of times that humans have witnessed. The odds of being in the right dune on the right morning are vanishingly small, and still it happens. The sky, given enough centuries, eventually does almost everything it can do. Picture the moment. A camel driver wakes before dawn. The air is colder than it should be. He steps outside and sees the red sand dusted in pale white, soft as powdered sugar, glowing faintly under a gray sky. By midday, it is gone, melted into the sand, leaving no trace except in his memory and a few photographs. The desert returns to being a desert. The snow returns to being a story. And somewhere in the upper air, the cold pocket that brought it drifts on, unexplained, looking for the next warm place to surprise. Picture yourself standing in a wide, quiet field at the edge of summer. The grass is soft underfoot. The sky above has turned a strange shade of green-gray, the color of an old bottle held against the light. Somewhere far overhead, hidden inside the swelling tower of a cloud, something is being built. Layer by layer, in slow, patient turns, a stone of ice is growing. Hailstones begin as tiny specks, a bit of dust, perhaps, or a frozen drop the size of a pinhead. The wind inside a thunderstorm lifts that speck up into the cold heights, where it gathers a thin coat of ice. Then it falls, drifts, gets caught in another updraft, and rises once more. Each trip adds a new layer. If you slice a large hailstone in half, you can see those layers like the rings inside a tree. Some rings are clear and glassy. Others are cloudy and white. The clear bands form when the stone grows slowly in warmer air, where water has time to spread before freezing. The cloudy bands form fast in colder pockets, trapping tiny bubbles of air inside the ice. Most hailstones stay small, the size of a pea, a marble, a coin. But every so often, the sky produces something else. A stone the size of a plum. A stone the size of an apple, and in rare cases, stones the size of a softball or larger, weighing as much as a heavy book. The largest hailstone ever officially measured in the United States fell in South Dakota in 2010. It was nearly 8 inches across and weighed close to 2 pounds. If you held it in your palm, it would feel impossibly cold and impossibly heavy. A jagged crystal sculpture pulled out of the upper sky. What puzzles meteorologists is not the small hail, but the giants. The math of updrafts can usually explain a stone the size of a golf ball. The wind inside a strong thunderstorm can hold something that heavy aloft long enough to build it. But the very largest stones, the ones with strange spiked points and unusual lobes, sometimes seem to grow faster or larger than the storm should allow. One theory suggests that certain supercell storms create rare pockets of slow, smooth lift, regions where a stone can hang almost motionless for many minutes, gathering ice in calm conditions. Another theory points to collisions, where smaller hailstones meet and fuse mid-flight, becoming the strange knobby clusters that sometimes land on roofs and lawns. Then there are the truly odd cases. Stones so large they seem to belong to a different category altogether. Lumps of ice the size of melons that crash through roofs in places far from any active thunderstorm. Scientists have a name for these. They call them megacryometeors. Unlike hail, megacryometeors fall from clear or nearly clear skies. They are made of layered ice, much like hailstones, but they sometimes weigh more than 50 pounds. Where they come from remains an open question. Some researchers wonder if they form in unusual high-altitude conditions where moisture freezes around a slowly falling particle over many hours. Others have suggested they may be linked to disturbances in the upper atmosphere that we do not yet fully understand. The honest answer is that no single theory has been proven, and the events are too rare to study easily. Imagine the surface of a field after a great hailstorm. The grass is flattened in patches. White stones lie scattered everywhere, half buried, half shining. Some are smooth and round like marbles. Others are strangely shaped, with little spikes and bumps, almost like small frozen sea urchins. smells clean and metallic. Steam rises faintly from the warm ground where the ice is already melting. If you knelt down and picked one up, you might see those internal rings glowing from within, each layer telling a small story about a journey inside the storm. Yet, for all the stones we have collected, weighed, and sliced open, the giants remain only partly understood. We can model a thunderstorm. We can map its winds with radar. We can predict in a rough way where hail might fall. But the exact path of a single rogue hailstone, the one strange enough to land in a museum, still slips through our equations. The atmosphere keeps a little chaos tucked inside every storm. So tonight, while the world is calm and the sky outside your window is quiet, you can rest with that thought. Somewhere in some patient cloud, a small speck of dust may be beginning a slow climb. What it will become and how large it might grow is a question the sky has not yet answered. Wind is the part of weather we feel most often, and the part we understand least when it begins to behave strangely. On a calm afternoon, with no storm in sight, a sudden gust can rise from nowhere, bend the tops of trees, and vanish just as quickly. These wandering bursts of moving air are some of the quietest mysteries in the study of weather. They leave no clouds behind. They leave no rain. They leave only the puzzled questions of the people who felt them pass. Meteorologists have names for many of these unexplained winds, though the names do not always come with full explanations. There are mountain winds that pour down slopes in the middle of the night, warm and dry, melting snow that should not melt. There are sea breezes that travel far inland and then suddenly reverse, as if changing their minds. There are dust devils that spin up in cool weather when the textbooks say they should not form at all. Each one hints at something happening above us that we cannot quite see. One of the strangest is the phenomenon known as a wind gust under clear skies, sometimes called a clear air gust. Researchers have measured these events for many decades. They arrive without warning. They carry no temperature change a person can easily feel. They appear on instruments as sudden spikes in air movement, then fade. One theory is that these gusts are the remains of distant storm outflows, traveling along invisible boundaries in the lower atmosphere. Another theory holds that they come from small pockets of sinking air, dropping down from layers high above. The honest answer is that some gusts fit one theory, some fit the other, and many fit neither. Deeper still is the question of how wind moves through the layers we cannot see with our eyes. The atmosphere is stacked like a slow ocean, with rivers of air flowing at different speeds and different heights. Near the ground, friction slows the wind. Higher up, the wind runs faster and smoother. Between these layers, hidden currents twist and shear against each other. When they meet, they sometimes spill downward in surprising ways, sending a quiet burst of motion to the surface below. There is a kind of wind called a downburst, and within that family lives the microburst, a column of cold air that drops swiftly from the base of a cloud. Pilots have come to know them well. They form quickly. They can knock down trees in patterns that look almost like the work of a small tornado. Yet they spin outward instead of inward. Microbursts are understood in broad terms, but predicting exactly when and where one will fall is still difficult. Two clouds that look nearly identical may behave in opposite ways. One drifts harmlessly. The other releases a sudden plunge of air that flattens a forest in seconds. Stranger still are the winds that move through valleys at night, carrying scents and sounds from great distances. In some mountain regions, people describe hearing distant rivers, distant bells, even distant conversations, carried over many miles by these cool nighttime flows. The air acts like a lens, bending sound waves along its layers. The exact paths these winds take and the way they fold sound through the dark remain a topic of careful study. There is also the question of katabatic winds, the cold winds that pour down off ice sheets and high plateaus. In parts of Antarctica, these winds can blow for weeks without pause, reaching speeds that would seem impossible if no one had measured them. They form when dense, cold air slides downhill under its own weight. The basic mechanism is known. The fine details are not. Why do some katabatic winds suddenly slow, then surge again, in patterns that no model predicts cleanly? Some researchers believe the answer lies in the shape of the ice beneath the air. Others suspect the role of small temperature waves rolling through the atmosphere above. The question remains open. Listening to descriptions of these winds, one begins to picture the air as a hidden ocean with its own deep currents, its own quiet tides, its own places where the water turns over and rises again. We live at the bottom of that ocean. We feel only the lowest ripples. Far above us, layers slide past each other in slow rhythms we are still learning to read. For tonight, it is enough to think of the wind as something with more depth than it seems. The next gust at your window may have traveled a great distance to reach you. It may have come from a storm 100 miles away, or from a quiet shift in the sky no instrument noticed. The air keeps its own secrets and shares them only sometimes. The sky changes color in cycles older than memory. Each morning it warms from black to blue. Each evening it cools back through gold and rose into deep violet. We see this every day, and yet the colors that arrive in the sky are not always the colors we expect. Sometimes the air turns green before a storm. Sometimes a low sun paints the clouds in shades that seem almost unreal. Some of these colors we understand. Others still puzzle the people who study them. Start with the simplest cycle. Sunlight is white, but it carries every color folded inside it. When that light passes through the air, the shorter blue waves scatter in all directions. That is why the daytime sky is blue. When the sun sits low, the light travels through more air to reach us, and the blues scatter away before they arrive. What remains is red, orange, and gold. So the sky burns warm at sunrise and sunset, then cools back to blue by midday. This rhythm repeats every day on every part of the planet that has air. Yet the sky does not always follow the script. After a great volcanic eruption, sunsets can glow for months in colors that feel borrowed from another world. Fine ash and tiny droplets of acid rise high into the upper air. They scatter light in unfamiliar ways. After the great eruption of Krakatoa in the late 1800s, observers around the world wrote of skies the color of copper and blood. Painters tried to capture it. The colors lasted years. Each volcano writes its own version of this slow, fading cycle, and no two are quite the same. Green skies belong to a different rhythm. During the warm months in certain parts of the world, tall thunderclouds build up through the afternoon. As the sun lowers, its reddish light passes through the deep blue water and ice inside the cloud. Red plus blue can give a strange greenish glow. Many people who live near tornado country know this color well. They watch for it. They feel uneasy when it arrives. But meteorologists still debate exactly what the green tint tells us. One idea is that the color signals a storm heavy with hail. Another is that it only signals a storm thick enough and tall enough to filter the light in that way. Both ideas may be partly right. The question is not fully closed. Then there are the red skies of dust. Winds lift fine sand from deserts and carry it across oceans. When that dust mixes with the slanted light of evening, the sky can flush a deep rust color, sometimes for days in a row. The dust follows seasonal patterns. It rises and falls with the cycle of trade winds and pressure belts. People in distant coastal towns learn to expect a certain kind of pink dawn at a certain time of year. They may not know that the sand above them was blown from a desert thousands of miles away. Some color cycles run on far longer clocks. During very cold winters, high in the polar regions, thin clouds form in the stratosphere. They are made of tiny ice crystals far above the weather we know. When the sun sits just below the horizon, these clouds catch the light and glow in soft pearls of pink, green, and gold. They are called nacreous clouds, and they appear only when the upper air drops to extreme cold. Some winters bring many, some bring none. The rhythm depends on patterns we are still learning to read. There is also the quiet, steady cycle of twilight itself. In the minutes after the sun drops, a soft band of pink sometimes appears in the eastern sky, with a darker blue beneath it. The pink band is the last sunlight catching dust high above. The dark band below is the shadow of the earth itself, cast against its own atmosphere. This happens every clear evening, and yet most of us never notice it. What ties all these colors together is that the air is always sorting light. Daily, seasonally, after eruptions, during dust seasons, in the cold polar dark. Each cycle leaves its mark on what we see when we look up. Some of the colors we can fully explain. Others, like the strange green of a heavy storm, still hold questions inside them. Tonight, somewhere on Earth, a sky is turning a color no one has named. A traveler is pausing to look at it. They may never know why it appeared, only that it did, and that it will fade, and that the cycle will begin again tomorrow. Fog is one of the gentlest forms of weather, and also one of the strangest. It sits low to the ground, soft and quiet, hiding the world inside a pale gray hush. We tend to think of it as simple. Tiny water droplets, suspended in cool air, drifting where the wind suggests. Yet fog has neighbors. It touches forests, coastlines, valleys, and cities. And in those meetings, it can behave in ways that look almost alive. Along the coast of Northern California, a thick marine fog rolls in from the Pacific each summer. It does not arrive like rain. It creeps. It pours over the hills like a slow river, finding gaps between the ridges, pooling in valleys, climbing up the trunks of the giant redwoods. Those redwoods, some of the tallest trees on Earth, drink that fog. Their leaves catch the moisture, and the droplets gather and fall to the soil below. Scientists studying these forests have measured how much water the trees collect this way. The fog feeds them. Without it, the redwoods might not grow so tall or live so long. That alone is curious, but there is more we still do not fully understand. Researchers have noticed that some fogs seem to move in patterns that do not match the wind. They flow uphill when the breeze is going down. They linger in one valley while a neighboring valley stays clear. They split around obstacles and rejoin on the other side, almost like a slow, soft fluid with a mind of its own. The most likely explanation is that fog is shaped by tiny differences in temperature and pressure that we cannot easily see. Cold air sinks, warm air rises, and fog rides those invisible currents. Yet, meteorologists admit that predicting exactly where a fog bank will go remains very difficult. Some fogs behave as expected. Others surprise even the people who study them for a living. There is a place in the deserts of coastal Peru and Chile where fog plays an even stranger role. The Atacama is one of the driest deserts on Earth. In some spots, rain has not fallen in living memory, and yet plants grow there. They survive on a fog called the Camanchaca, which drifts in from the cold ocean and settles against the dry hills. Tiny droplets cling to leaves and stones. Whole small ecosystems live entirely on this misty breath from the sea. Lift the fog away, and the desert would have no life at all in those pockets. How a fog can sustain an entire community of living things in a place that otherwise should be empty is a question that still draws researchers back year after year. Then there is the fog that seems to listen to the land. In parts of Newfoundland, where the cold Labrador current meets the warmer Gulf Stream, fog forms so thick that ships have vanished from sight within their own length. Sailors there speak of fogs that seem to follow a boat, or to part briefly and then close again. The science behind it is simple enough at one level. Warm, moist air passes over cold water, and the moisture condenses into countless tiny droplets. But the local shapes of these fogs, the way they bunch and stretch and travel, are still hard to model. Even modern forecasts struggle to predict exactly when and where the thickest banks will appear. Inland, fog meets a different neighbor, the forest itself. In the cloud forests of Costa Rica, Ecuador, and parts of Southeast Asia, fog wraps the trees almost daily. Mosses and ferns drink directly from the air. Frogs lay their eggs in the wet film on broad leaves. Whole species of insects and birds depend on the constant humidity. If the fog rises just a little higher up the mountainside, the forest below begins to dry out. Some researchers wonder whether shifting climate patterns might lift these fog layers permanently, leaving the lower forests starved of moisture. Others think the fog will simply adjust, finding new heights where the conditions still suit it. The honest answer is that no one yet knows for certain. What ties all of this together is the way fog refuses to be just one thing. It is weather, and it is water, and it is also a kind of slow companion to the landscapes it visits. It feeds trees. It carves out tiny gardens in deserts. It hides ships and shelters frogs. It moves in ways that follow rules we partly understand and partly do not. Tonight, as you rest, you might picture it. A soft gray tide rising into a quiet forest, settling among the roots of trees that have been waiting all morning for it to arrive. Somewhere over a wide stretch of plains, on a quiet evening when most of the world is settling down, a single bolt of lightning stretches across the sky. It does not flash and end. It keeps going. It travels across one state, then another. It crosses rivers and small towns and sleeping fields. By the time it finishes its long, branching walk through the clouds, it has reached farther than the distance between many capital cities. This is a megaflash, and it is one of the strangest extremes in all of Earth's weather. For most of human history, no one knew these giant lightning strikes existed. People watched the sky from the ground, and from the ground, a bolt looks short. You see the flash above your head. You hear the thunder. You assume the lightning lives and dies in one small patch of cloud. But satellites changed that. When sensitive instruments began watching storms from above, they saw something almost impossible to believe. Single flashes that stretched for hundreds of miles. Single flashes that lasted for many long seconds. Lightning that wandered across the sky like a slow, glowing river. The current record holder is a megaflash measured over the southern plains of the United States. It stretched for more than 477 miles. That is roughly the distance from one end of a small country to the other. Another megaflash, recorded over South America, lasted more than 17 seconds in a single continuous discharge. Most ordinary lightning bolts finish their work in less than a tenth of a second. These giants linger. They drift. They reach. How does this happen at all? The honest answer is that no one fully understands it. Researchers know that megaflashes only seem to form inside certain massive storm systems, especially the wide, flat, sprawling thunderstorms that meteorologists call mesoscale convective systems. These storms create huge sheets of cloud where the electric charge can spread out over enormous distances. One theory is that megaflashes are simply ordinary lightning given an unusually large playground. The flash finds a long, smooth pathway through the cloud and follows it for as long as the path holds together. A competing view suggests something more particular is going on. Some researchers wonder whether megaflashes need a specific kind of layered charge structure inside the storm. In this idea, the cloud must build up sheets of positive and negative charge at just the right heights, separated by just the right gaps, before a single discharge can run that far. If this is true, megaflashes are not just big versions of normal lightning. They are a different beast that needs rare conditions to wake up. Which theory is closer to the truth is still being worked out. Even the basic counting of megaflashes is uncertain. The satellites that watch for them have only been doing this work for a short stretch of years. Older storms went unmeasured. We do not know how often megaflashes happened in the past, or whether they are becoming more common as the climate shifts. Some scientists suspect that warmer air and bigger storm systems may give megaflashes more chances to form. Others are not sure the data is long enough yet to draw any firm conclusion. The question waits patiently for more years of watching. There are other extremes hiding in the world of lightning. 2. The hottest part of a bolt can briefly reach temperatures hotter than the surface of the sun, heating the surrounding air so quickly that it explodes outward as the sound we call thunder. The tallest lightning travels upward, not downward, climbing from the tops of thunderclouds into the thin air far above. The slowest lightning crawls inside a cloud, glowing softly, never striking the ground at all. And then there is volcanic lightning, born inside the ash plumes of erupting mountains, sparked by some process involving colliding particles of rock and ice that researchers are still trying to fully describe. What all these extremes share is a quiet humility on the part of the people who study them. The scientists who chase megaflashes do not pretend to have the whole picture. They speak carefully, with words like probably and seems, and one possibility. They know that the sky has been making lightning for billions of years, and that humans have only been looking up with sensitive instruments for a few decades. Tonight, somewhere on Earth, a megaflash may be drawing its slow, glowing line across a sleeping continent. No one beneath it will see the full shape of what passed overhead. Only a satellite watching from far above will record the long, patient reach of a single bolt. And even then, the deepest question of how it came to be remains open, suspended in the dark and quiet air. High above the Atlantic, in a layer of warm, dry air the pilots call the Saharan air layer, a quiet river of dust drifts west. It rides the trade winds for thousands of miles. The grains are tiny, often smaller than the width of a human hair. Some are smaller still, fine enough to slip into the lungs without a sound. And yet, in this fineness, there is something beautiful that scientists return to again and again. Each grain began somewhere in the Sahara, lifted by a gust off a dry lake bed or a parched riverbed. Many come from one small basin in Chad called the Bidele Depression. It is one of the dustiest places on Earth, and it once held an ancient lake the size of a small sea. The dust there is rich in old plankton skeletons, ground to powder over thousands of years. When the wind picks them up, those tiny skeletons begin a long ride across the ocean. The journey can take 5 days or 7 or more. The dust rises into the dry layer of air above the moist trade winds, and there it sits, suspended, like flour drifting through a slow shaft of sun. From space, the plumes look soft and pale, curling out over the Atlantic in long ribbons. Some plumes are so wide they shade entire islands. Some thicken the air over Florida and Texas, turning sunsets the color of warm copper. What the scientists find most quietly astonishing is what the dust does when it lands. Across the Atlantic lies the Amazon rainforest, one of the wettest places on Earth. Its soils are old and washed thin by constant rain. They need phosphorus, the mineral that helps plants grow. And year after year, the Saharan dust delivers it. Tiny grains, lifted from a vanished African lake, settle on the leaves of trees half a world away. One desert feeds one rainforest across an ocean in silence. How much phosphorus the dust actually carries, and how much the rainforest truly depends on it, are still open questions. One estimate suggests tens of thousands of tons land in the Amazon each year. Another suggests far less, depending on the rainfall that washes the grains down. Some researchers wonder whether the connection is steady or whether it shifts with each passing decade. The link is real, but the size of it remains uncertain. The dust does other quiet things, too. It seems to suppress hurricanes, drying out the air they would otherwise feed on. It seeds clouds, giving water droplets something to gather around. It tints the rain, a faint reddish brown when it falls back to earth. The so-called blood rain that has fallen on rooftops in Spain and France and Britain for centuries. Old villagers once spoke of it as an omen. The grains themselves are simply travelers finishing a long ride. Under a microscope, the dust reveals its small wonders. Some grains are shaped like rough crystals with sharp, clean edges. Others are rounded, polished by tumbling against each other in the wind. Some carry hitchhickers, bacteria, fungal spores, even tiny fragments of plant matter. Researchers have found living microbes that survived the entire crossing, riding the dust like passengers on a slow ship. Whether those microbes take root on the other side and what they do when they arrive is something biologists are still trying to understand. The dust storms themselves can be enormous. A single plume may stretch farther than the width of the continental United States. Yet from the ground, in the middle of one, the world simply turns hazy. The sky goes pale yellow. The sun becomes a soft disk you can look at without squinting. The air smells faintly mineral, like an old stone wall after rain. People who live downwind of the Sahara know this haze well. People in the Caribbean have grown used to it. People in the Amazon never see it land, only the slow greening that follows. What scientists cannot yet fully predict is which storms will carry their dust the farthest, and why some years bring great plumes, while others bring almost none. The patterns shift with rainfall in Africa, with wind speeds, with the shape of distant pressure systems. There are models that work well most of the time, and models that fail in surprising ways. The dust keeps its own quiet schedule. It is a strange thought to hold in the dark, that the rainforest you have seen in photographs is fed by a desert you have never visited, that a lake bed which dried up long ago still sends gifts across an ocean. That so much of Earth's weather is this: small grains, long journeys, slow connections we are only beginning to trace. High above us, far beyond the clouds we know, there is a quieter layer of air called the stratosphere. It begins about 10 kilometers up and reaches almost 50. It is cold and dry and mostly still. And every few winters, something very strange happens there. The temperature in just a few days can leap upward by 50 degrees Celsius or more. The story of how humans noticed this hidden event is a slow and patient one, built from balloons, paper charts, and quiet rooms full of careful watchers. For most of human history, no one knew the stratosphere even existed. The sky was simply the sky. Sailors read the wind on the surface. Farmers read the clouds. The upper air was a place of imagination, not measurement. That began to change in the late 19th century when a French meteorologist named Léon Tesserent de Bort started sending small unmanned balloons high into the air, each one carrying a tiny instrument that recorded temperature as it rose. He expected the air to keep getting colder the higher his balloons climbed. For a long while, it did. Then, around 10 kilometers up, the cooling stopped. The temperature held steady and sometimes even climbed. He repeated the experiment hundreds of times before he trusted what he was seeing. In 1902, he announced that the atmosphere had 2 layers, not one. He called the lower part the troposphere, the place of weather and turning air. He called the upper part the stratosphere, the place of stillness. The world of meteorology had just doubled in size. For decades after that, the stratosphere was thought to be a calm and predictable place. It was cold, it was quiet, and it seemed to do very little. Then, in the winter of 1952, a German meteorologist named Richard Scherhag was studying balloon data over Berlin. He noticed that the temperature high above the city had jumped upward in a way that made no sense. In a matter of days, the upper air had warmed by tens of degrees. There was no storm to explain it. No sunlight strong enough at that time of year. Nothing in the lower atmosphere that should have pushed so much heat upward. Shurhag thought at first that his instruments must be wrong. He checked them carefully. Then he checked the readings from other stations. The warming was real, and it was huge, and it had happened in the dark heart of winter. He published his findings, and the event was given a name that has stuck ever since. Sudden stratospheric warming. Once people knew to look for it, they began to find more examples. The warmings did not happen every year, but they happened often enough to be studied. Sometimes the polar vortex, that great spinning ring of cold air over the Arctic, would slow down or even reverse direction during these events. Sometimes, weeks later, the surface weather across Europe and North America would turn unusually cold and snowy. The connection between the high warming and the low chill became a puzzle that meteorologists are still working through. There are two main ideas about what causes a sudden stratospheric warming to begin. One is that giant waves of air rising up from mountain ranges and large weather systems below push energy into the stratosphere and break the vortex apart. Another idea is that internal instabilities in the vortex itself can tip it into chaos without any clear trigger from below. Both ideas have evidence supporting them. Neither fully explains why some winters bring a major warming and other winters bring nothing at all. The instruments have improved enormously since Shurhag's day. Weather balloons still rise twice a day from stations all over the world, carrying sensors no bigger than a sandwich. Satellites watch the upper air from above, measuring temperatures across whole continents at once. Computer models try to predict the warming's days or weeks in advance. They sometimes succeed. They sometimes do not. What remains genuinely open is the deeper question of how the stratosphere talks to the surface. We can see in the records that a sudden warming in January often leads to bitter cold in February. But the chain of cause and effect runs through layers of air we cannot easily feel, and the timing is loose, and the strength of the link changes from one event to the next. Some researchers wonder if a warming climate will make these events more common. Others wonder if it will make them rarer. The answer has not arrived. A century ago, the stratosphere was a blank page. Now It is a page covered in careful writing, with margins still full of question marks, waiting for the next quiet observer to notice what the rest of us have missed. Of all the strange shapes weather can take, few feel as impossible as a column of spinning fire. A fire whirl is exactly what it sounds like. A swirling tower of flame, smoke, and burning air that rises from a wildfire or a burning field. Some are small, no taller than a person. Others stretch hundreds of feet into the sky, roaring like a furnace, glowing orange against the smoke. They look like something from a dream, and yet they are real, and they happen more often than most people realize. The basic recipe seems simple. Hot air rises from a fire. As that hot air lifts, cooler air rushes in to take its place. If the surrounding winds are turning even slightly, that motion can tighten into a spin. The spin pulls flame upward, stretching it into a long, twisting column. It is a little like the swirl of water draining from a sink, only made of fire and ash and shimmering heat. That much meteorologists understand well. What still surprises them is how strong these whirls can become. Most are short-lived, lasting only a minute or two. But a few have grown into something far stranger. Researchers sometimes call these larger events fire tornadoes, though the name is debated. A true tornado forms from the base of a thunderstorm, born in the clouds and reaching down. A fire whirl usually forms from the ground up, born in the flames themselves. The question of whether the two can merge, whether a fire can grow tall enough to make its own true tornado, is still being studied. There is one famous case that pushed the question into new territory. In 2018, during a wildfire in Northern California, a rotating column of fire became so powerful that it produced winds estimated near 140 miles per hour. It tore trees from the ground and twisted steel power poles. Weather radar showed a clear signature, almost identical to the signature of a regular tornado. Some researchers now believe this event was a true fire-generated tornado, not just a tall fire whirl. Others remain unsure. The line between the two remains blurry, and the data is still being studied. The colors inside these whirls are also strange. Most fires glow orange and yellow, but fire whirls sometimes appear pale blue at the base, where the burning is hottest and the air is being pulled in fastest. That blue flame is a sign of nearly complete combustion. Some scientists have recreated this in the lab, generating small, slow-burning blue whirls that float quietly over a pool of fuel. These laboratory whirls burn cleaner and more efficiently than ordinary flames. Whether that finding could ever be useful for cleaner burning, for example, is an open question. The size question is also unsettled. Historical accounts describe fire whirls that may have reached over half a mile high. After the Great Kanto earthquake in Japan in 1923, fires swept across the city, and witnesses described enormous spinning towers of flame moving through the streets. The accounts are striking, but they were written long before modern instruments existed. We cannot measure those events now. We can only wonder how tall, how fast, and how hot they truly were. Even the smaller whirls hold puzzles. They sometimes appear in places with no obvious wind shear. The twisting of wind at different heights that usually helps spin them up. They sometimes form on calm days in the middle of a quiet burn with no clear trigger. Researchers have set fire to small experimental plots and tried to predict when whirls will appear. The whirls often refuse to cooperate. They form when the equations say they should not, and stay absent when the equations say they should. There is also the question of sound. People who have stood near large fire whirls describe a deep, low roar, almost like the engine of a jet. The sound seems to come from the column itself, from the rushing of air and the burning of fuel. But the exact mix of frequencies and why some whirls roar while others whisper has not been fully mapped. For all that fire whirls are studied, they remain hard to catch. They appear in dangerous places, often deep inside wildfires where instruments cannot easily go. Most of what we know comes from photographs, lucky radar images, and small experiments in controlled rooms. The largest, strangest, most powerful ones may be visiting Earth more often than the record shows, simply because no one is close enough to measure them. A column of flame spinning under a smoky sky is one of the oldest images of awe in human memory. though we have learned much about how such a thing can rise, the upper limits of its size, strength, and shape are still being slowly, carefully understood. There is a kind of rain you may have seen without knowing it. It falls from the belly of a cloud in long, soft streaks, like gray hair brushed downward by the wind. The streaks reach toward the earth, thin and trailing, and then they simply vanish. The rain stops in midair. Nothing arrives below. Meteorologists call this virga. The word comes from an old Latin term for a slender branch or rod, which is how these falling shafts often look against a darkening sky. Virga is rain that gives up before it lands. It can also be snow, or tiny pellets of ice, or any falling moisture that evaporates while still in flight. The cloud weeps, but the ground stays dry. What makes virga interesting is not the falling, but the failing. To understand why rain sometimes never arrives, you have to think about what sits between the cloud and the ground. That space is not empty. It is a long column of air, and that air has its own temperature, its own dryness, its own restless movement. Rain has to survive the trip. If the air below the cloud is very dry, the falling drops begin to lose themselves into it. Each drop gives up a thin layer of water as vapor. The drop shrinks. If the column of dry air is deep enough, the drop can disappear completely before it ever touches a leaf or a roof. The cloud above keeps producing rain, and the dry air below keeps erasing it. The two systems are in quiet conversation, and the conversation decides whether anything reaches us. This is one of the gentler ways that weather shows its connections. A storm is never just a storm. It is a cloud, and the air beneath the cloud, and the heat rising from the land, and the moisture carried in from a distant sea. Change any one of those, and the outcome shifts. Virga is what happens when the cloud is generous and the lower air refuses the gift. There is more to it than vanishing water. As the drops evaporate, they pull heat out of the surrounding air. Evaporation cools. A long shaft of virga can chill a pocket of air high above the ground, and that cooler, denser air can then sink. It sinks fast, sometimes very fast. When it reaches the surface, it spreads outward in a sudden burst of wind. Pilots know this kind of wind. It is called a downburst, and it can be dangerous near runways because it appears out of a sky that looked, from below, almost calm. So the rain that never lands can still touch the ground in another form. It arrives as wind instead of water. The cloud sends a message, and the message becomes a gust. This is one of the small, hidden ways the sky talks to itself. How often this happens, and exactly how strong these hidden downbursts can get, is still a question with rough edges. Forecasters can spot Virga on radar because the falling moisture reflects the radar beam. But predicting whether a given shaft of Virga will cool the air enough to launch a downburst, and how severe that downburst might be, is harder. Some studies suggest the dryness of the middle atmosphere is the key factor. Others point to the size of the drops, or the depth of the cloud, or the temperature gradient below. The truth likely involves all of these at once, in proportions that vary from storm to storm. Virga also connects to bigger patterns. In deserts and high plateaus, where the lower air is often parched, Virga is common. Clouds may pass overhead all afternoon, trailing their useless ribbons, while the land below stays cracked and thirsty. The same cloud, drifting later over a wetter region, might finally release its rain. The cloud has not changed. The air beneath it has. There is something quietly moving about this. A cloud builds itself over hours, gathering vapor from 100 small sources. It rises, cools, and condenses. It begins to rain. And then, depending on what lies below, the rain either becomes a river, or a puddle, or nothing at all. The story of any single raindrop is the story of every layer of air it had to pass through. When you watch Virga from a distance, you see the whole connection laid bare. The cloud, the falling streaks, the empty space, the dry valley floor. Each part is part of the same system. None of them work alone. The sky writes in long sentences, and Virga is one of the softer punctuation marks, a trailing thought, a pause, a phrase that does not quite finish before the next one begins. High above the storms we know, far above the rain and the rolling thunder, something else flickers in the dark. It does not look like ordinary lightning. It does not crackle down toward the ground. Instead, it rises. It blooms upward into the thin air above the clouds, glowing in colors of red and blue and faint green, fading almost as soon as it appears. For most of human history, no one knew it was there at all. These quiet, high-altitude flashes go by gentle names: sprites, elves, blue jets, halos. Each one is a different shape, a different burst of light, lasting only a few thousandths of a second. A sprite can spread across the sky like a soft red jellyfish, with long trailing tendrils drifting down toward the storm below. A blue jet shoots upward in a narrow cone, like a quiet flame reaching for the stars. An elf is a flattened ring of light that expands outward in a perfect circle, vanishing before the eye can fix on it. For a long time, pilots whispered about these flashes. They saw strange glows above thunderclouds during long night flights across oceans and continents. Their reports were often set aside, gently doubted, filed away as tricks of tired eyes. Scientists assumed that all the lightning of Earth went downward, from cloud to ground, or sideways, from cloud to cloud. The idea of lightning going up into the calm air far above the weather did not fit the picture. Then, in 1989, a camera at a university in Minnesota caught one by accident. The researchers were testing their equipment, pointed at the night sky for an unrelated experiment. In one frame, a strange column of light hovered above a distant storm. That single image opened a door that had been closed for centuries. Within a few years, cameras on aircraft and on the International Space Station began catching more of them. Sprites and their cousins were real. They had always been real. We simply had not been looking. Even now, the mechanisms behind these silent flashes are not fully understood. One leading idea is that a very powerful bolt of cloud-to-ground lightning, the kind that carries an unusual amount of charge, sets up a brief electric field reaching high into the upper atmosphere. That field, the theory goes, excites the thin gases above the storm, causing them to glow softly for a fraction of a second. The red color of a sprite in this view comes from nitrogen molecules releasing their energy in a particular way. Other researchers wonder whether tiny cosmic particles or stray electrons drifting in the upper air play a larger role than we realize. They ask whether the spark that starts a sprite begins not in the storm below, but in a chance encounter high above, where a single fast particle triggers a cascade. The competing ideas are not enemies. They may both be partly right. The honest answer is that we are still piecing the picture together, one slow flash at a time. What makes this part of the story belong to change is how new it all is. Sprites and elves have been firing above our heads for as long as there have been thunderstorms on this planet. They have been quietly painting the sky above Earth for millions of years. Yet, our understanding of them is only a few decades old. The map of Earth's weather, which we sometimes imagine as complete, keeps growing in directions we did not expect. The changes continue even now. Newer cameras can record these events in extraordinary detail, capturing shapes that were never seen before. Researchers have noticed faint, slow-moving glows that drift for longer than a sprite should last. They have spotted features within the flashes, small beads of light, fine branching structures, ghostly halos that surround the main event. Each new observation raises new questions. Each new question gently pushes back the edge of what we know. There is something soothing in this. The sky is not finished revealing itself. The storms that rumble far away tonight, somewhere on the dark side of the planet, are almost certainly sending up these silent flashes that no human eye will ever see. They bloom and fade above the clouds in their quiet red and blue, witnessed by nothing but the thin air and the occasional satellite. The Earth keeps its secrets gently in plain sight, just above where most of us are looking. And so, the picture of high-altitude lightning keeps growing slowly. Year by year, image by image, we learn a little more, then a little more. The full shape of it still lies ahead, somewhere in the patient work of cameras pointed at the night, waiting for a flash that has not yet been named. There is a strange kind of light that lives inside a hurricane, not the gray light of a normal storm, but something heavier, slower, almost amber at times. Pilots who have flown into the eye of certain great storms describe a quiet column of sun pouring straight down through a hole rises around them like a stadium made of white vapor, lit gold at the top, gray at the bottom, and for a few minutes, the world inside that ring is calm, blue, and impossibly bright. Most hurricanes follow patterns that meteorologists have learned to read. Warm ocean water feeds them. Wind shear weakens them. Cool water and dry air starve them. But every so often a storm does something that the rules say it should not do. It strengthens when it should fall apart. It turns when no steering current explains the turn. It holds together over land. It speaks a language the models cannot quite translate. One of the strangest features is something called rapid intensification. A storm sits at modest strength one evening with winds that seem manageable. By morning, it has become a monster. Its winds doubled, its pressure plunging. The mechanism is partly understood. Warm water in the upper ocean, low wind shear, and a well-formed inner core all help. But not every storm with those ingredients explodes, and some storms explode without all the ingredients in place. Why one storm crosses that threshold and another does not is still an open question. Some researchers wonder whether tiny processes inside the eye wall, processes too small for current models to capture, hold the answer. Others suspect that the deep ocean below the surface matters more than we have given it credit for. The light inside the eye has its own puzzle. Sailors and pilots over the centuries have reported a rim of strange color around the eye wall at sunset. Pink, copper, sometimes a deep rose that fades into violet. The color comes from sunlight bending through immense walls of moisture. The same physics that paints any sunset, but stretched and intensified by the storm's geometry. The eye becomes a kind of natural cathedral, with windows of cloud catching the last of the day. We can describe the light. We cannot always predict when an eye will form clearly enough to show it. History remembers certain storms that broke their own forecasts. A storm in the late 19th century that turned hard toward a coast no one expected. A storm in the mid-20th century that crossed cool water and refused to weaken. A storm that wandered in a loop for days, drifting against the prevailing winds, as if held in place by an invisible hand. In each case, the meteorologists of the time did their best with the tools they had. In each case, the storm did something the tools could not see. Even today, with satellites watching from above and buoys listening from below, some tracks still surprise us in the final hours. One idea is that hurricanes are sensitive to conditions far away. A pocket of dry desert air drifting off a distant continent. A pulse of warm water rising from below. A jet stream wobble thousands of miles away. The storm becomes a kind of giant ear, listening to the whole atmosphere at once, responding to signals we have not learned to read. Another idea is that the chaos sits inside the storm itself, that the swirl of small thunderstorms around the eye behaves in ways that are mathematically unpredictable beyond a certain point, no matter how good our instruments become. Both ideas may be partly true. The full picture is not yet clear. And then there is the quiet question of color over land. After a hurricane passes, the light in the air often looks different for a day or two. The sky takes on a washed, pale quality, as if rinsed clean. Dust and salt and bits of forest hang in the upper air. Sunsets afterward can be unusually vivid, deep orange smudged with green at the horizon. The storm leaves behind a fingerprint of particles, and the light passing through that fingerprint tells a story of where the storm has been. We have learned to name these storms, to track them, to give them numbers and categories. But naming is not the same as knowing. Each hurricane is its own atmosphere, its own slow argument between heat and water and wind. Some follow the script we have written for them. Others rewrite the script as they go, and in the amber light at the heart of the eye, or in the strange pale sky that follows the storm out to sea, there are questions still waiting in the quiet for someone to ask them. Listen for a moment to the sound of a field in winter, not the loud sound of wind through bare trees, but the smaller sound underneath, a soft creaking, a faint hiss, the papery rustle of snow shifting against itself. In certain rare conditions, a meadow can begin to make a sound it does not usually make, a gentle rolling sound, a whisper of crystals tumbling slowly across an open plain. This is the sound, some witnesses say, of snow rollers forming. A snow roller is one of the strangest small wonders the weather makes. It looks like a log of snow or a hollow wheel lying on its side in an open field. Some are no bigger than a tennis ball. Others grow as wide as a car tire. They appear after a particular kind of storm, when a thin layer of wet, sticky snow falls on top of a slick base of ice or older powder. Then the wind must come, but not too hard. Just hard enough to nudge a small piece of snow into motion. Once that little piece begins to move, something quiet and lovely happens. The snow picks up more snow as it rolls. The inside layers, which were the first to gather, often collapse and fall away. What remains is a hollow tube, like a soft scroll of paper left in the grass. The wind keeps pushing. The roller keeps growing. And across a single field, dozens or hundreds of these natural sculptures can appear in a single morning, all rolled by the same patient breeze. The sound of their making is almost too soft to hear, a faint sliding, a tiny brushing of snow on snow. People who have stood in the right field at the right hour describe it as a kind of quiet activity, as if the meadow were softly busy with something it did not want to disturb you about. Much of the snow roller is understood. Meteorologists know the rough recipe. They know the kind of snow that works, the kind of base it needs, the rough speed of wind that helps. What remains less clear is why some storms produce thousands of rollers, and others, in seemingly identical conditions, produce none at all. The exact threshold, the precise tipping point, has not been fully mapped. One idea is that small differences in humidity change how sticky the top layer becomes. Another is that the shape of the land, the gentle dips and rises, decides whether a rolling motion can begin at all. The question is open in the small ways that quiet questions often are. The ice circle is a stranger cousin. On certain slow rivers in winter, a perfect disk of ice will appear, sometimes a few feet wide, sometimes larger than a house. The disk spins, slowly, smoothly, almost as if a hand beneath the water were turning it. The sound of an ice circle is the sound of the river itself, the soft gurgle of cold water beneath, and the faint grinding of the disks edge against the rim of still ice that surrounds it. For a long time, ice circles were thought to be made only by swirling currents, by little whirlpools that broke a chunk of ice free and then rotated it in place. That theory still holds in part, but a more recent idea suggests that the spinning is not driven only by water moving below. It may be driven by the disk itself. As ice melts, it releases cold water into the river. That cold water sinks. The sinking creates a tiny downward current right at the edge of the disk. That current, some researchers wonder, may be enough to make the whole circle slowly turn, like a lazy carousel powered by its own melting. Both theories may be partly right. Both may be incomplete. Different ice circles on different rivers may form for slightly different reasons. The grinding edge, the soft scraping of disk against shore, is one of winter's quieter mysteries. What is shared by snow rollers and ice circles is a certain patience. They do not arrive with thunder. They do not announce themselves. They appear in the morning after a still night and surprise the people who walk out to find them. Their sound is the sound of weather working quietly, without spectacle. The sound of snow turning over in a field. The sound of a slow disk turning on a slow river. We can describe these events. We can list their conditions. But we still cannot perfectly predict when a meadow will fill with rollers, or when a river will spin a perfect circle of ice. They remain among the small, unfinished questions of weather. Beautiful, patient, made of nothing more dramatic than wind, snow, water, and a kind of quiet that allows them to form it all. On the cold edges of the polar seas, the water does something strange. It does not freeze into one flat sheet. Instead, it forms thousands of round disks, each one floating beside the next, each one rimmed with a soft white edge. From above, they look like a great floor of pale dinner plates, packed close together, drifting slowly with the swell. This is pancake ice. It is one of the most quietly beautiful patterns Earth makes, and the math inside it is gentle, simple, and not yet fully understood. The disks form when small bits of slushy ice gather on the surface of moving water. As the waves rise and fall, the slush bumps against itself again and again in a slow, circular rhythm. The edges of each clump get pushed upward, forming raised lips. The middles stay flat. Over hours, each lump rounds itself into a near-perfect circle, the way a stone tumbles smooth in a river. The size of each disc tends to fall within a narrow range, often between 30 centimeters and 3 meters across. Why that range, and not larger or smaller, is part of the open question. One idea is that the size depends on the length of the waves passing through. Longer waves, longer disks. Shorter waves, smaller disks. The math of this is elegant because it ties the size of the ice to the rhythm of the sea itself. If you know the wave period, you can roughly guess the disk size. Some researchers have measured this in the Antarctic and found the pattern holds, more or less. Others have found exceptions, where the disks are too small, or too large, or too uneven for the wave theory alone to explain. A second idea suggests that the temperature of the water and the salt content matter as much as the waves. Colder water makes thicker slush, which rounds faster. Saltier water freezes at a lower point, which slows the whole process. The combination of these numbers, wave period, temperature, salinity, may set the final shape. The trouble is, no one has fully solved the equation. The variables shift constantly, and the ice does not wait for the math to catch up. There are other frozen patterns whose numbers are even stranger. Ice circles form on calm rivers, slow round plates that rotate gently in the current. Some are only a meter wide. Others grow to over 100 meters, turning so slowly you cannot see the motion with your eye, only with a long camera exposure. The rotation seems to come from the way cold, dense water sinks beneath the disk, dragging it in a soft spiral. The shape stays circular because the edges melt evenly. The geometry is simple. The exact balance of forces is not. Then there are the hexagons. In some shallow Arctic ponds, ice forms in 6-sided cells, like the chambers of a honeycomb, each one bordered by a thin ridge. The pattern echoes shapes seen elsewhere in nature, in basalt columns, in soap foam, in the cracked floors of dry lakes. The reason is something called close packing, a quiet rule that says circles pressed together will arrange themselves into hexagons, because that shape wastes the least space. The math is old, and it is the same math that bees use, and that bubbles use, and that mud uses when it dries. Earth keeps returning to this number, 6, in places that have nothing else in common. What remains open is why some patterns appear and others do not, in conditions that look nearly identical. Two stretches of ocean, side by side, both freezing, both cold. One forms pancakes, the other forms a smooth sheet. Researchers have measured currents, winds, temperatures, and still the answer slips away. The math is almost there, but a few variables remain hidden, perhaps in the structure of the water itself, perhaps in the tiny particles drifting through it, perhaps in something not yet named. There is comfort in this. The numbers are simple. The shapes are simple. Circles, hexagons, gentle ratios between size and wave. Yet the full equation has not been written. Somewhere between the slow turn of an ice disk and the steady rhythm of a polar swell, Earth is keeping a small piece of the answer to itself. For tonight, it is enough to picture them. A wide, cold sea, dark beneath a low gray sky. Thousands of pale disks drifting in slow patience, each one rounded by the same patient motion, each one a small piece of geometry the planet drew without being asked. The math is there. The mystery sits softly inside it, waiting for someone someday to finish the page. There is a sound that some people hear on clear, calm days when no storm is anywhere in sight. A low rumble, soft as distant furniture being moved in another room. The sky above them is blue or barely streaked with cloud. Yet something in the air has spoken, and they pause, unsure whether they truly heard it. This is sometimes called thunder without storms, or cryosysm, or simply a sky boom. The names shift because the explanation shifts. Sometimes the rumble comes from the ground itself, when frozen soil cracks deep below the surface. Sometimes it comes from far above, from a storm so distant the clouds are hidden beyond the curve of the horizon. And sometimes, even after careful study, no clear cause is found at all. The atmosphere that carries these sounds is astonishingly thin. If you shrank the Earth down to the size of an apple, the layer of air that holds our weather would be thinner than the apple's skin. Every cloud, every breeze, every roll of thunder happens inside that delicate film. The fact that sound can travel through it for hundreds of miles, bending around temperature layers like light through water, is itself a quiet wonder. One theory for these unexplained booms is that sound from a thunderstorm can be carried far beyond its visible reach. When warm air sits above cooler air, it forms a kind of invisible ceiling. Sound waves bounce along this ceiling and travel much farther than they normally would. A storm 100 miles away might whisper its thunder into a town where the sky looks perfectly clear. Some researchers think many mystery booms are exactly this distant weather, ducted along the upper air like a voice down a long hallway. Another idea points downward instead of outward. In very cold regions, water seeps into the ground and freezes. As ice expands, it can crack the soil with a sudden snap that sounds like thunder. These cryocisms are real and documented, mostly in winter, mostly in places where the ground freezes deeply, but they cannot explain the booms heard in warm seasons or near coasts where the ground rarely freezes at all. A third possibility lives offshore. Methane bubbles trapped beneath the seabed sometimes rise and release with a low rumble. Waves striking certain underwater cliffs can produce deep pulses that travel inland through the air. The sea, in its slow churning, may speak in tones we only sometimes catch. Yet not every coastal boom has a clear ocean source, and inland booms cannot be blamed on waves at all. What makes this mystery so gentle is how it depends on the precise balance of our atmosphere. If the air were thicker, sound would carry differently, and these distant rumbles might be common and unremarkable. If the air were thinner, like the wisp of atmosphere on Mars, thunder itself would barely exist, muffled into near silence. Our planet sits at a strange middle point, where the air is dense enough to carry voices for hundreds of miles, but thin enough that those voices arrive softened, mysterious, easy to doubt. The temperature layers matter too. Earth's atmosphere is built in stripes, each warmer or cooler than the one above it. These stripes act like lenses, bending sound and light in ways that depend on the season, the time of day, even the humidity. A boom that travels easily on a still autumn morning might vanish entirely by afternoon, when the lower air warms and the acoustic ceiling lifts away. There is something humbling in this. The same sky that brings us soft rain and golden sunsets is also a kind of vast, listening instrument, capable of carrying secrets from places we cannot see. We hear a sound, we look around, we find nothing, and we are left with the simple, lovely fact that the air itself has memory and reach and behaviors we have only partly mapped. How delicate is this balance? Consider that the speed of sound in air depends on temperature. Consider that a difference of just a few degrees, spread across miles of altitude, can decide whether a thunderclap dies quietly or travels halfway across a country. Consider that the very chemistry of our atmosphere, mostly nitrogen, with just enough oxygen to keep us alive, and just enough carbon dioxide to keep us warm, sets the conditions for every sound we have ever heard outdoors. Change any of these variables a little, and the world would sound different. Change them more, and the world might not hold us at all. So when a soft rumble drifts in from a clear blue sky, with no storm to claim it, the mystery is not only where the sound came from. The mystery is also how an atmosphere this thin, this fragile, this the weather we see today is only a thin slice of what the sky has done. Earth is very old. The air above us has shifted through warm ages and cold ages, through times of choking dust and times of soft, steady rain. And in all that long history, there were storms no human ever watched. Storms whose shapes we can only guess at from the marks they left in stone. Geologists sometimes find clues in old rock layers that hint at weather we cannot easily picture. Ripple patterns frozen into ancient sandstone. Raindrop dimples preserved from a single afternoon billions of years ago. These tiny marks survived while mountains came and went. One quiet question runs through all of it. Did the weather of deep time work the way it works now? Or did it follow rules we have not yet learned to read? Take the early Earth. when the air held far more carbon dioxide and almost no oxygen. The sky may have looked orange or hazy pink, lit by a younger, dimmer sun. Some researchers think the rain back then fell in huge, warm sheets, soaking everything for days at a time. Others wonder if much of the planet was capped in clouds so thick that sunlight rarely touched the ground. Both ideas fit the rocks in some places and not in others. The truth probably sits somewhere between, and somewhere we have not yet imagined. There were also long stretches when Earth seems to have frozen almost entirely. Scientists call these the snowball Earth events. During those ages, ice may have reached from the poles all the way to the equator. The weather inside such a world is hard to picture. With oceans locked under ice, the sky would have grown very dry. Storms may have been thin, cold, and rare. Yet some thinkers wonder if huge dust storms scoured the frozen plains, kicked up by winds with nothing to slow them. Others believe quiet was the rule, with whole centuries passing under still, pale skies. The rocks hint at both and disagree with themselves. Then came the great thaws, when the ice broke apart and warm rains returned. Some models suggest the rebound was violent. Hurricanes larger than any we know today may have spun across newly opened seas. Lightning could have flashed in storms that lasted for months without pause. But other researchers think the warming was slower and gentler, with mist and drizzle returning before the first real thunderstorm rolled in. We can model these scenes on computers, yet the models pull in different directions depending on which numbers we trust. The deep past holds other puzzles too. There are hints of mega droughts that lasted thousands of years, drying out whole continents. There are hints of mega monsoons that flooded river valleys for generations. Some ancient sand dunes preserved in stone are so large that the winds which built them must have been steady and strong for ages. What kind of climate produces winds like that? We are not sure. The patterns do not match any modern place on Earth. Even closer to our own time, weather has done strange things. During the last ice age, parts of the world swung between cold and warm spells very quickly. Sometimes within a single human lifetime. Why those swings happened, and how the storms changed during them, is still being worked out. Ice cores from Greenland hold tiny bubbles of ancient air, and inside those bubbles are clues about wind patterns, dust loads, and storm frequency. Reading them is slow, careful work. Each new core adds a few sentences to a story that is millions of pages long. There may also have been weather events so unusual that they only happened once or twice in all of Earth's history. A single superstorm after a giant asteroid impact. A year of red skies after a vast volcanic eruption. A century of strange rains after a sudden shift in ocean currents. These one-time events leave faint traces, easily mistaken for something else. We may have walked past their evidence in the rock without knowing what we were looking at. What makes deep time weather so haunting is that no one will ever see it directly. We can only listen to what the stones whisper, and the stones, being patient, give up their secrets slowly. Each year, new tools let us hear a little more. Yet the question stays open. The sky above the dinosaurs, the sky above the first lichens, the sky above the first single cells. Each of those skies had its own moods, its own storms, its own quiet days. Most of those days are lost forever. A few left fingerprints, and we are still learning gently how to read them. Out on the warm water, far from any harbor, a thin column of mist sometimes rises from the surface of the sea. It curls upward in a slow spiral, joining a low cloud above. The wind around it is gentle. The water below it dimples and dances. This is a waterspout, one of the strangest and most quiet of all spinning storms. And even now, no one can fully predict when one will appear. Waterspouts come in two main kinds, and the difference matters. The first kind forms under a strong thunderstorm, much like a tornado on land. It is loud and dangerous, and behaves in ways meteorologists have studied for decades. The second kind, sometimes called a fair-weather waterspout, forms under far gentler skies. It rises out of calm water beneath soft, puffy clouds. Why it forms at all is still partly an open question. One theory points to small lines of wind that meet at the sea surface. Where these breezes collide, billowing cloud above can stretch this turning into a slender funnel. Another theory adds a role for warm patches of sea, where rising air pulls upward like a soft chimney. Both ideas explain part of what is seen. Neither fully explains why one warm afternoon makes a spout, and the next, with the same look and feel, makes none. In 1,000,000 years, the seas will still spin these quiet columns into the sky. The coastlines will have shifted. Reefs that stand today may lie deep beneath new water. Islands that have not yet risen will host warm, shallow bays where waterspouts dance by the dozen on summer mornings. The shapes of the spouts will be the same. The mystery, very likely, will be the same too. In 100,000,000 years, the continents will have drifted into new arrangements. Some scientists think the land masses may gather again into a single great supercontinent. The oceans around it will be vast and warm. Such a sea would breed whether we can barely imagine. Waterspouts there might form in long lines, marching across the open water for days, born from storm systems with no land to break them. 1,000,000,000 years from now, the sun will shine a little brighter. The seas will be warmer still. Some models suggest the air above them will hold more water vapor than today. More vapor often means more spinning, more rising, more strange columns linking sea and sky. Whether waterspouts will be common or rare in that distant world, no one can really say. The basic recipe should still work. The details depend on a climate we cannot yet simulate. Further out in deep time, the picture grows stranger. As the sun ages and expands, the oceans will slowly thin and fade. Long before they vanish, the air will grow heavy with steam. In that hot, hazy world, the very last waterspouts may rise from shrinking salt seas under skies the color of old copper. They will be the final descendants of the gentle spouts seen today by sailors on quiet afternoons. No human eye is likely to see them. The physics, though, will run on without us. It is worth sitting for a moment with how old this pattern already is. Waterspouts almost certainly formed on the young Earth when the first wide oceans spread across a cooling crust. They spun above seas that held no fish, no coral, no boats. They formed for the same simple reasons they form now. A bit of warm water, a bit of moist air, a soft turning in the wind, and a low cloud willing to pull upward. The recipe is older than memory. What makes the future interesting is not that waterspouts will exist. It is that the questions about them may still exist. Forecasters today can sometimes warn of conditions that favor them. They cannot pick the exact bay, the exact hour, the exact spiral. The fair weather kind especially seems to slip between the rules. One idea is that the smallest pieces of the puzzle, the eddies and ripples no instrument can measure, decide where each spout is born. If that is true, perfect prediction may always be out of reach. For tonight, picture a warm coast 1,000,000 years from now, on a shore that has no name yet. The water is still and clear. A soft cloud sits low over the bay. From the surface, a thin column of mist begins to climb, turning gently, joining the cloud above. There is no one to wonder about it. There is no one to ask why this place, why this hour, why this spout, and not another. The mystery is patient. It will wait for whatever comes next. On certain summer nights, in the middle of the dark hours, the air over a sleeping town will suddenly grow warm. Not gently, not by a few degrees. In some cases, the temperature has climbed 20 or 30 degrees in just a few minutes, well past midnight, when the air should be cooling. The wind picks up. Leaves rattle on trees that had been still. And then, as quickly as it came, the strange warm pulse fades back into the ordinary night. Meteorologists call these events heat bursts. They are rare, they are local, and they remain only partly understood. The leading idea is that they form when a dying thunderstorm sends a column of dry air plunging down from high altitudes. As that air falls, it compresses, and compression warms it. By the time it reaches the ground, the air has heated itself through its own descent. That much fits the math. But the finer details, why some collapsing storms produce heat bursts and others do not, why some bursts last minutes while others last an hour, remain quiet, open questions. There are other warm winds in the world that carry their own puzzles. The Chinook winds slide down the eastern slopes of the Rocky Mountains and can raise temperatures so quickly that frozen ground turns to mud in a single afternoon. fun winds of the Alps do something similar. The Santa Ana winds of Southern California arrive hot and dry from the desert and bend the trees sideways. Each of these has a known mechanism, air warming as it descends a mountainside. And yet, each still surprises forecasters with the timing, the intensity, the suddenness of its arrival. And this brings us, in this quiet hour, to the widest view of all, because every one of these strange warm pulses, every sudden gust of midnight heat, is part of a story that began long before Earth itself existed. The air that warms a sleeping town tonight is made of nitrogen and oxygen and traces of older things. The oxygen came from tiny ocean plants that learned billions of years ago to take sunlight and split water and breathe out a new kind of gas. The nitrogen came from the slow outgassing of volcanoes, from rocks that themselves were forged in the hearts of long-dead stars. The carbon dioxide that helps trap warmth in the lower atmosphere carries carbon atoms that were once inside ancient ferns, inside ancient seas, inside the cooling crusts of worlds that no longer exist. The water that rides on these winds, the vapor that makes a thundercloud collapse and send its hot breath down to the prairie, is the same water that has been on Earth since the beginning. It has been a glacier. It has been a tropical rain. It has been inside the body of a creature that swam in a sea that no longer has a name. And tonight, some small fraction of it is in the air just outside your window, and some small fraction of it is in you. The calcium in your bones was made inside stars that exploded long before our sun was born. The iron in your blood was forged in the same fires. The atoms that make up the warm wind and the atoms that make up the listener of this voice came from the same vast cloud of dust that gathered slowly into a small rocky world with a thin shell of air. And so, when a heat burst rolls across a Kansas field at 2 in the morning, it is not really a stranger. It is the same matter that has been here all along, rearranging itself once more into something briefly warm, briefly strange, briefly worth wondering about. The wind that lifts the curtain is older than the curtain, older than the house, older than the town, older than the species that built the town. This is the perspective that the weirdest weather invites. Not fear, not alarm, just a quiet recognition that the sky above us is not separate from us. We breathe it. We are partly made of it. And it still does things regularly that the smartest people on Earth cannot fully explain. The heat burst will fade by morning. The town will not remember it. A few sensors will record the spike, and a few researchers will look at the trace and add it to a long, patient list of events that almost fit the theory and almost do not. The work will continue. The questions will remain open, and somewhere tonight, on some plain or some valley, a warm pulse of ancient air will move quietly through the dark, carrying with it a small piece of a story that began before anyone was here to wonder about it. And so the long night of weather has carried us gently to its quiet edge. We have stood beneath skies that rained fish and watched dust travel across whole oceans. We have listened for thunder where there was no storm and wondered at lightning that climbs upward into the dark. We have sat with whirlwinds of fire and with snow that rolls itself into soft white wheels across an empty field. Some of these things scientists understand. Many of them they still do not. That is the shape of weather in the end. It is older than us and stranger than us, and it does not wait for our permission to be strange. The air around you right now is part of a single restless ocean that wraps the whole planet. It moves in slow rivers and sudden gusts. It carries water and dust and the smell of distant rain. It has done this for billions of years. It will do it long after this night is forgotten. Think for a moment of the earth as it would look from very far away. A pale blue sphere slowly turning, white swirls of cloud moving across its face, the night side glowing softly where storms flicker over warm seas. The day side bright with deserts and forests, and the long curved gleam of the oceans. From that distance, every storm we have spoken of tonight is only a small bright detail, a tiny pinprick of lightning over a quiet sea, a pale brown smudge of dust drifting from one continent to another, a faint white shimmer of noctilucent cloud high above a sleeping town. And yet, inside each of those tiny details, there is a whole world, a fishing boat tipped by a waterspout. A village waking to a sky the color of rust. A child watching a single hailstone larger than a grapefruit rest in the grass after a summer storm. A scientist somewhere looking at a chart and frowning because the numbers do not yet quite add up. Weather is the place where the very large and the very small meet in soft collisions again and again. What we do not know about it is, in some ways, the most comforting part. The sky is not a solved problem. It is not a closed book. There are still mysteries above your roof tonight that no one on Earth has fully explained. Ball lightning still flickers in old stories and unverified photographs. Megaflashes still stretch across hundreds of miles of cloud, and no one is entirely sure why some grow so large. Sudden warmings still shake the stratosphere without quite the warning we would like. The atmosphere keeps a few of its secrets, even now. Maybe in your lifetime, some of these riddles will be answered. New satellites are watching. New instruments listen to the slow hum of distant storms. Researchers in quiet rooms compare notes from every corner of the planet. Year by year, the map of the unknown shrinks a little. And year by year, new strangeness appears at its edges. The sky seems to have a gentle rule about this. For every mystery solved, it offers another. For tonight, though there is nothing you need to solve, the weather will continue without you. The clouds will form and drift and break apart and form again. Somewhere on the planet, rain is falling on a forest no person has ever walked through. Somewhere else, snow is settling on a mountain in perfect silence. An ocean is rising and falling under a low moon. A desert is cooling, grain by grain, as the last warmth of the day slips away into the dark. You are part of all of this. The breath moving slowly in and out of you is the same air that has touched glaciers and storms and the wings of distant birds. The water in you has been rain and river and sea and cloud. You belong to the weather of this planet as much as any cloud does. And the planet, in its quiet, patient way, holds you. So let the questions stay open. Let the strange rains and the silent lightning and the spinning columns of sea all rest in their unfinished places. The sky does not need an answer tonight. neither do you. Let your thoughts drift the way fog drifts over a low field at dawn, soft and unhurried, going nowhere in particular. Let the long, gentle turning of the earth carry you the rest of the way into sleep. Somewhere above you, the air is doing something no one has ever seen before. And that is a beautiful thing to fall asleep beside. Subscribe for a brand new Earth topic every night. One tap, and something wonderful is waiting for you tomorrow. Sweet dreams.